A single locomotive weighs about 420,000 pounds, and yet somehow it drags a line of freight cars that can tip the scales at over 40 million pounds, stretching out for miles. And if that sounds like it should be physically impossible, that's because in almost every other machine you've ever seen, it is. Now here's the part that really messes with people. That locomotive isn't even 1% of the total weight it's pulling. And if you tried anything remotely similar with a truck or a bulldozer or even the biggest mining equipment on Earth, you just get spinning wheels and burned out components. So the real question isn't just how trains pull so much weight, it's why they're even allowed to get away with it in the first place, because what's happening here feels less like brute force and more like a perfectly engineered loophole in physics. The answer starts with something so simple it almost sounds boring, but it changes everything once you really sit with it, because every vehicle you've ever been in is constantly wasting energy just rolling forward, and that waste is called rolling resistance, where rubber tires deform against the road, flexing, heating up, and bleeding energy with every rotation. And for trucks on asphalt, that rolling resistance coefficient sits around 0.008, meaning for every 1,000 pounds of weight you're dragging along, about 8 pounds of force is just being burned to keep the wheels turning. Which doesn't sound like much until you scale it up to tens of thousands of pounds. Now compare that to a train where steel wheels meet steel rails with almost no deformation at all, and suddenly that coefficient drops to somewhere between 0.001 and 0.002. which is 4 to 8 times less resistance. And that's not just a small improvement. That's the difference between struggling to move and barely feeling the load at all. Because the contact patch where a train wheel touches the rail is about the size of a dime, maybe half a square inch, carrying tens of thousands of pounds with almost no energy loss, while a truck tire spreads out over nearly a full square foot, constantly squishing and flexing like a sponge under pressure. And here's the counterintuitive part that most people never think about. More contact area actually makes things worse for efficiency, because all that extra surface is just more material deforming and wasting energy, while the steel wheel just rolls cleanly with almost no give. And then that's exactly why trains can hit fuel efficiency numbers like 477 to 528 ton-miles per gallon of diesel, while trucks are stuck somewhere between 68 and 145 ton-miles per gallon, which means rail is easily 3 to 4 times more efficient at moving heavy cargo, and it all comes down to that one beautifully simple advantage of steel on steel. But even with that insane efficiency, you still run into a massive problem the moment the train is sitting still, because getting something moving is always harder than keeping it moving. And if a locomotive had to overcome the static friction of 100 fully loaded freight cars all at once, the force required would be so extreme, it would literally snap the couplers like breadsticks, which is why railroads rely on one of the smartest mechanical tricks you'll ever see. Something so subtle most people never notice it. Every coupler between freight cars has about 6 inches of free play built into it, known as slack. And inside each coupler is a shock-absorbing device called draft gear. So when a train is stopped, all those connections are loose. And on a 100-car train, that adds up to roughly 50 feet of total slack, which is basically 50 feet of stored opportunity. And engineers use it in a way that feels almost like cheating. Before moving forward, the locomotive actually backs up slightly to compress the entire train, bunching every car together so all that slack is pushed out. And then when it starts pulling forward, it doesn't try to move the entire train at once. Instead, it pulls the first car, then the second, then the third, and so on, with the motion rippling down the line like a slow zipper opening. Which means instead of needing something like 200,000 pounds of force in a single instant, the locomotive only has to overcome about 2,000 to 3,000 pounds at a time per car, spreading that force over several seconds instead of one impossible moment. Once the train is moving, the next challenge is grip, because even with low resistance, you still need the wheels to push against the rails without slipping, and this is where adhesion comes into play, which basically defines how much of the locomotive's weight can be converted into pulling force. And for steel on steel, that coefficient usually sits between 0.25 and 0.40 under good conditions, meaning a locomotive can generate pulling force equal to 25% to 40% of its own weight before the wheels start spinning. So when you look at something like a 420,000 to 432,000 pound locomotive, that translates into a starting tractive effort of roughly 189,000 to 200,000 pounds, which is almost half its body weight being turned directly into forward pull. And what makes it even more fascinating is that the geometry of the locomotive actually helps it out, because the coupler sits about 30 inches above the rail, while the axles are at rail level. And that offset creates a torque effect that shifts weight onto the rear driving wheels as the locomotive pulls harder, effectively increasing traction exactly when it's needed most. Of course, real-world conditions aren't always perfect, and things like rain, oil, or even crushed leaves can drop that adhesion coefficient down to 0.10 or 0.20, cutting pulling power in half, which is why locomotives carry sand on board. And when traction starts to slip, they drop that sand directly onto the rails in front of the wheels, creating tiny rough points that boost friction back up. And it's such a simple solution that it's been used for over a century because nothing has really beaten it. Modern locomotives take it even further with computerized wheel slip detection systems that monitor every axle in real time. And the moment a wheel starts spinning faster than the others, the system reacts within about 10 milliseconds, cutting power to that axle and redistributing it to the ones with better grip, which means the locomotive is constantly operating right at the edge of maximum adhesion without crossing into uncontrolled slip. And all of this happens faster than a human could even react. Then there's the part that surprises a lot of people. The diesel engine in a locomotive doesn't actually drive the wheels at all. Instead, it powers a generator that produces electricity. And that electricity feeds traction motors mounted directly on each axle, turning the entire locomotive into a rolling power plant. And this matters because electric motors can deliver maximum torque at zero speed, which is exactly what you need to start moving something incredibly heavy without burning out components like a traditional transmission would. At around 10 miles per hour, a 4,300 horsepower locomotive can produce roughly 161,000 pounds of tractive effort, and as speed increases to 50 miles per hour, that force drops to about 32,000 pounds, but the horsepower stays the same, smoothly shifting from pulling power to speed without any gear changes, which is why locomotives don't need transmissions at all, and that simplicity is a huge part of their reliability. The real leap forward came in the 1990s, when AC traction motors replaced older DC systems, because DC motors relied on brushes that physically contacted moving parts, creating friction, heat, and sometimes even fires, while AC motors eliminated those issues and allowed precise computer control over each wheel, improving adhesion by 20% to 30%. And the impact was massive, with railroads finding that 3 AC locomotives could do the work of 5 older DC units on heavy trains, effectively cutting equipment needs by around 40% in some operations. As trains kept getting longer, another challenge emerged because pulling everything from the front created enormous stress on the couplers, which max out at around 750,000 pounds of force. So railroads started placing locomotives throughout the train, with configurations like 4 in the front, 2 in the middle, and 3 at the rear, all controlled remotely, distributing the forces along the entire length and allowing trains to stretch beyond 2 miles with over 200 cars without tearing themselves apart. And while getting a train moving is impressive, stopping it is where things get genuinely intense, because a 10,000-ton train moving at 50 miles per hour carries an enormous amount of kinetic energy, and relying only on traditional brakes would quickly overheat and destroy them, which is why locomotives use dynamic braking, where the traction motors reverse their function and turn into generators, converting motion back into electricity that gets dissipated as heat through resistor grids on the roof, sometimes producing enough heat to visibly shimmer in the air. Newer systems are pushing this even further, with battery-assisted locomotives like those equipped with around 7 megawatt-hour batteries and 3.2 megawatts of traction power, roughly equivalent to 4,290 horsepower, capturing that braking energy instead of wasting it, and achieving double-digit reductions in fuel consumption, which shows how the technology is still evolving even after more than a century. When you zoom out and compare trains to everything else, the scale becomes almost absurd, because a typical semi-truck maxes out at around 80,000 pounds gross weight and maybe carries 20 tons of cargo, while a single freight train with just 2 crew members can move 10,000 tons or more, achieving costs of roughly 1 cent per ton mile, and replacing about 300 trucks on the road, which isn't just an efficiency advantage, it's an entirely different level of logistics. And the craziest part is that all of this power doesn't come from one single breakthrough. It comes from layers of smart engineering stacked on top of each other, from low rolling resistance and clever use of slack to adhesion physics, electric drive systems, and distributed power, all working together so seamlessly that what looks impossible at first glance becomes something railroads do every single day without much attention. So next time you see a freight train stretching out over the horizon, just remember that you're not looking at brute strength. You're looking at one of the most elegant combinations of physics and engineering ever put into motion. And it raises a question that's honestly hard to ignore. If something this efficient has existed for decades, why don't we apply the same level of thinking to more of the machines around us? And what would transportation look like if we did? If you made it this far, I'm curious what surprised you the most. Was it the idea that a locomotive only pulls one car at a time, or the fact that trains are 3 to 4 times more fuel efficient than trucks? And if you enjoy breaking down how things actually work, instead of just watching them happen, stick around and consider subscribing, because there's a lot more hidden engineering like this that most people never get to see.